Question 9. There are several stages in industrial production of methanol from methane. The first stage involves a gaseous equilibrium between the reactants methane and steam and some gaseous products. Figures 1 and 2 show the percentage conversion of methane into the gaseous products under different conditions at equilibrium. We've got figure 1, we've got figure 2. To deduce the optimum conditions for industrial conversion of methane and steam into the gaseous products, explain your deductions. 6 marks. Okay. Well, usually for the 6 markers there is 3 stages. The first stage in this question is going to be deduction the optimum conditions. Stage 2 is going to be the optimum temperatures and explanation, and stage 3 is going to be the optimum pressure and the explanation. So the optimum conditions. Well, let's have a look at the figures. So the optimum temperature, well, it increases, and then here. Now the optimum pressure temperature is not 900 degrees C, it's somewhere here, because this is when it starts to plateau. So I'd say 800 degrees Celsius, 780 to 800 degrees Celsius. So let's just say 790 degrees C, because you don't really need that 800, because that's when it's starting to peak a bit. 790 is fine. For the optimum pressure, well, the optimum pressure is going to be, because as we increase pressure, the percentage conversion decreases, which you don't want it to increase. So the optimum pressure is going to be 1000 to 2000 kilopascals. In this case, let's just say 1010 kilopascals. So let's write this down. So we know deductions from graph. Well, we know the yield increases, yep, as the temperature increases. As temperature increases, we also know after a certain temperature, yield no longer increases. And for the pressure one, we know yield decreases as pressure increases. Yield decreases as pressure increases, or you can say pressure decreases, or yeah, yield decreases as pressure increases. That's fine. So this is stage 1. Actually, I'll just separate the stages. Stage 2, optimum temperatures and explanation. Well, we know high temperature means high energy cost, hence expensive. You can't just say high temperature, therefore it's expensive. High temperature, high energy cost, expensive. Just an extra bit of, that writing will give you the extra marks in the exam, especially for these type of wordy questions when you're looking at a graph and then you're basically finding out key details and why does that happen. We know after a certain temperature, yield no longer increases, hence no point in because if the yield is no longer going to increase, there's no point of using a higher temperature. And then the optimum temperature is 780 to 800 degrees. Let's just say 790 degrees Celsius. Now for pressure, well, we don't want to increase pressure. We do not want to increase pressure, because we know yield decreases, pressure increases. However, at low pressures, extremely slow reaction could take years, 10 years, and obviously you don't want that to happen. So we're going to have to compromise pressure required. So we're not going to, do less than 1,000, because if you look at the graph, it looks like if you do less than 1,000, it'd be at 100, but it'll take too long. So we can't do that, and it's not even on the graph, so it's, yeah. So we're gonna have to optimum pressure is 1,010 kilopascals, or 1,000 to 2,000 kilopascals, whatever. So this is stage 1, stage 1, this is stage 2, and this is stage 3. Stage 1, deduction from graph, and then the optimum temperature and the explanation, optimum pressure and explanation for 6 marks. 9.2, and we also got 9.3, 6 marks again. So 9.2, equations of the final state production methanol, blah blah blah, 20.1 moles of carbon monoxide, 24.2 moles of hydrogen placed in CO container. The equilibrium was established at 600 Kelvin. Equilibrium mixture contained 2.16 moles of methanol. Calculate the amount in moles of carbon monoxide and of hydrogen in the equilibrium mixture. So what we're going to use is that method called MCE. I think it's, but for me, I think the best way to do this is just draw a table, even though it is 2 marks. But the idea is you got your moles. I'm pretty sure it's this way. And you got your equilibrium moles. And we've got 3 elements, what we're going to call it. So we don't really need this 4th thing, so let's cross that out. So we've got carbon monoxide, hydrogen, and we've got methanol. And we know 20.1 moles of carbon monoxide, so that's the moles, and 24.2 moles of hydrogen placed in CO container. Equilibrium was established at 600 Kelvin. The equilibrium mixture contains 2.16 moles of methanol. So methanol, we've gone to 2.16. E standing for equilibrium moles, C standing for change in moles, and M just moles. So we've gone from 0 to 2.16, so plus 2.16. Because it doesn't tell us in the question, we're going to assume it is 0. Now if we're increasing 2.16 this way, we're going to have to decrease 2.16 this way, so it's going to be minus 2.16. This is going to be minus 2.16, but because we've got 2 moles times by 2, so it's going to be 24.2 minus 2.16 times by 2, 19.88 of hydrogen, 19.88, and for this carbon monoxide, 20.1 minus 2.16, 17.94, 18.94, 19.88. Then this is a different mixture of carbon monoxide and hydrogen was allowed to reach equilibrium at 600 Kelvin. Equilibrium mixture contained this many moles of carbon monoxide, this many moles of hydrogen, this many moles of methanol. Total pressure was that. Calculate value for Kp for its reaction at 600 Kelvin and state its units. So Kp, partial pressures, equals, I confuse myself with KP and KC, but KP is round brackets, so of products CH3OH, yeah, we should know this, CH3OH, 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 yeah, over reactants, partial pressure reactants, carbon monoxide, times by partial pressure of hydrogen squared, because there's 2 moles of it. Now we know the total moles of gas, let's write T is equal to, well, it's just going to be this plus this plus this. Seven point six three moles. Or we can draw a table, which I'm going to do. Carbon monoxide, hydrogen, methanol, and we don't need the equilibrium moles, we already know the equilibrium moles. At equilibrium, mixture contains this many moles. We want to know the mole fraction, so we're going to write mole fraction mole fraction carbon monoxide 2.76 over 7.63, because that's the moles of carbon monoxide over the total moles. Hydrogen 4.51 over 7.63, and methanol 0.360 for 7.63. And now for the now we need to times by the pressure, 630 kilopascals. So we're going to times by the pressure times by 630 times each of these mole fractions by 630. Probably should have done it in a separate box, but it's fine. And now we'll get the values. So 2.76 over 7.63 times by 630. 228, just round it, 228 kilopascals pressure. 4.51 over 7.63 divided by 630. 372 kilopascals and 0.360 over 7.63 divided by 630. 29.7 kilopascals. Now we're almost done. We know Kp equals partial pressure of round curly brackets of methanol, which in this case is going to be 29.7 over of carbon monoxide 228 times by hydrogen squared, partial pressure of hydrogen squared, 372 squared. And then just put it here. So 29.7 228 times by 372 squared, 9.41 times by 10 to the power of -7, and the units, well, we've got kPa over kPa times by kPa squared, kPa cubed, units. Therefore we get 1 over kPa squared. Because kPa squared is in the denominator, it's going to be kPa to the power minus 2. kPa to the power minus 2. That's the end of question 9. That's for 6 marks.